Hi, y'all. So I'm going to go through the group work for chapter 17 in preparation for your quiz tomorrow. So the first question is label the electrophilic carbon in each molecule and rank from least to most electrophilic. So the electrophilic molecule in a carbonyl compound is always going to be right there at the carbon-oxygen double bond. All that is the electrophilic spot because there is this resonance structure that exists where this is partially positive, and we know resonance is actually more like a hybrid of these, so this is partially positive when it exists just in this state. Sorry for the shadows. I'm in kind of a poor lighting situation. Let me see if I can actually make it a little bit better. I don't actually know how much that helped, but we're just going to roll with it because I'm already all set up here. Okay, so the other thing you have to consider is electron density. So electron density and electron donating groups. So if you have this partial positive right here, you could either have things that donate electrons towards that positive to help stabilize it and make it less reactive. Or you can have things that take away positive charge, like that leave more positive even than they started with. So like a strong electron withdrawing group, like a nitro, would do this same sort of thing. So if you had that, that would make it less stable, and things that are less stable are more likely to react. So really what we're looking at is what on here is going to be stabilized by electron donating groups, making it less reactive, less electrophilic, react more slowly, and what is destabilized by electron withdrawing groups and what will make it less stable. Okay, sorry, I got interrupted. I'm just going to pick off here where I left off. So, yeah, if it has electron donating groups, that's going to make it more stable. It's putting electrons into that partial positive. But if it has something that's pulling electrons away, electron withdrawing, that's taking electrons away from that partial positive, making it less stable. And less stable, it's actually more likely to react, right? Like, just think about like a human being. If you're someone who's less emotionally stable, you're going to have a stronger emotional reaction. And I can say that because I'm not as emotionally stable. So I do have stronger reactions when I'm not being stabilized by something like my medication, right? So if it's not being stabilized by something, or if it's under stressful conditions that are even taking away from its stability, it's more likely to react. So if you need to tell yourself like that to help you remember, you totally can do that. Okay, so now let's ask, so which one of these have electron donating or electron withdrawing groups? So this is electron withdrawing, right? Chlorine is electron withdrawing by the inductive effect. It's one of the most withdrawing ones. And then, so this is an electron withdrawing group. This ester has electrons it's donating in, so that's a donating group, electron donating group. This amine is also a donating group, electron donating group. So you've got 3 electron donating groups. Oh, sorry. This is also electron donating. So you have 3 electron donating groups. So when I look at this, I'm automatically like, this is the most reactive, no question. And then I think amines are going to be the next most reactive. Actually, oh, maybe not. I think I might have said that backwards. I think the esters are going to be the next most reactive. Like, I think it goes this and then a neutral one, or if there's like a carbon there, and then esters and then amines. So I always get like my most to least mixed up. I have to like check myself. But this is going to be able to donate to some degree. This is donating half as much, right? Because it's split between both of those. So I would actually say that the next most reactive, the next that's like most least stable, the less stabilized is going to be this one, because it has an electron withdrawing group on it, but it actually it has an electron donating group on it. Sorry, it is so late right now. And my brain, I have not been sleeping enough because I've been working a lot. So my brain is like kind of slow, but it has electron donating group, but it's split between two electrophilic centers. So instead of just donating fully in one electrophilic center, it's actually split. And then this is also electron donating to some degree, but not as strongly as the amine group. The amine group is more strongly electron donating. And this actually follows the same trend that you have for your aromatic rings, right? So like if you had an NH2 group that was more activating than an alcohol group on your aromatic rings, it's kind of the same thing. It's the same type of concept for electron drawing or electron donating on this carbonyl carbon. Okay. I'm actually going to skip over question 2 for 2 reasons. One, we went over this in class. Dr. Corrales went over all of the main connections that you need to know. I think it was like from here to here, here to here, here to here, here to here, 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 here. I don't remember if you have to go from NH2 to aldehyde. And then from this or this, and then from here to here. I think those were the main ones, but we did go over it in class. Oh, and then you need to be able to go from here to here, here to here, here to here, here to here, all the things. And then all of these, you need to know how you can hydrolyze them back. And I also did a video very similar to that that's already posted. So I'm not going to go over this in detail since we already went over it. Okay, and next, name or draw the following compounds. Use the common name where applicable. I'm going to be honest, nomenclature at this level is kind of one of my weaknesses just because we use the common names more often than we use the IUPAC names. And I didn't use a lot of these molecules in my own research. So for me, I'm so sorry. This is actually sort of an area of weakness of mine because it's like, well, you just kind of have to know them. But for carboxylic acids, those are kind of easy. You do whatever this R group is and you name it however you would name it. And then you can just say carboxylic acid for the common name. And then for the IUPAC name, I actually think you just replace it with like oic acid. So it'd be like cyclopentanoic acid. That's the IUPAC name. And usually, Dr. Corrales doesn't really test you on the names themselves as much, but the biggest reason you need to be able to recognize names is if you're like on an exam or the ACS exam, you're going to have to be able to recognize. I'm so sorry. You're going to have to be able to recognize the IUPAC name or the common name. So this next one, succinic acid. Oh, I'm sorry. This is actually succinic anhydride. The reason it's called succinic anhydride is because this is formed from a reaction with succinic acid with itself. Let's see. It's 1, 2, 3, 4, a 5-membered ring. So this reacts with itself. This is succinic acid. It'll react with itself, and then that means it loses this OH and H, which is water. So it's lost a water, and anhydride means absence of water. So you've probably actually seen this also in skincare. At times in skincare products, it'll be like such and such anhydride. That literally means without water. The Ordinary has an anhydride product that is oil-based, not water-based. Okay, and then the next one, propionyl chloride. If you ever see prop in any way, it's going to be 3, so you can start with that. And then you know it's probably going to be a chloride, right? And then usually if there's an ional, propionyl, that means that there's going to be a ketone of some kind, but this is a common name. I think if you were naming this in the IUPAC name, it would actually be propanoyl chloride. So that's actually, I kind of know the oils, like OYL, propanoyl, better. So you replace the E with OYL. And you've also probably seen this in like benzoyl peroxide. Benzoyl peroxide is probably my favorite skincare product. I think this is the structure. So it's a benzene ring with a peroxide on it, right? It actually might, I think this is a structure, but it might look like this. Either way, this is my favorite skincare product because it's it causes oxidative stress and it's really good at like killing bacteria. So it's really good as an antibacterial. And the reason it does that is because this breaks up and it forms radicals, and you can't have too many radicals in your cell. But I think because of that kind of thing, I actually have the oil more in my brain than the common name. And then malonic acid is actually one that you're going to see a lot in the upcoming chapter. And it really is just two carboxylic acids that are one away from each other. And you're also going to start to see malonic esters as well. So malonic acid, malonic esters, that's something that you probably are going to see more often as we go forward. So it's worthwhile to learn that. But as long as you just focus on being able to recognize and recreate the names that Dr. Corrales has gone over in class, you should be fine with that. I honestly I struggle with memorizing things. Y'all know that. Everything I pretty much do in the course, I do from like having learned the concepts and less about the memorizing. And I feel like these names don't have a system that I can like work through as well. You just have to learn the IUPAC name for the functional groups themselves, and then you have to just like memorize the common names. It just kind of sucks. So that's my thought on that. This next one is about acidity, and something that I think is really important for acidity, and I've done this in other videos, but for acidity, you can think of like how willing is it to give up this proton, right? Like how willing is this proton to leave? But something that's actually easier for me to think of is how stable are the electrons that are left behind? So it's hard for me to just look at like alcohol or this carboxylic acid and know off the top of my head which proton's easier to leave. But if I look at this epoxide, like the O minus and the carboxylic acid that's lost a proton, it's pretty easy for me to see like, oh, this carboxylic acid, the electrons will come up here and it'll go like this, and this has a resonance structure. And this alcohol doesn't have a resonance structure, so this is more willing to give up a proton because the electrons here are more stabilized, right? So the same thing goes for this question right here, where we're talking about ranking the acids in order of increasing acidity. What I'm thinking for all of these is if we have this carboxylic acid, it's lost that proton. Let's get rid of the proton for all of it. And now I'm just wondering which one of these is going to be able to handle extra electrons the better. Well, if you're trying to handle extra electrons better, more resonance is better, and also pulling electron density away is better. And we've seen that before with the inductive effect. There's always like a question like this in the early chapters where it's like, which one of these is better, right? Like, which one of these is more acidic? And this is more acidic because those fluorines have strong electron withdrawing properties, so they'll pull the electrons towards them and stabilize the electrons that's left behind. So again, we're just looking at what's going to be able to stabilize those electrons. So what's going to do that? And pulling electrons away is going to be better. So in this case, electron withdrawing group is going to be more stable. And you can't just memorize like, oh, electron withdrawing group is always going to be more stable, because we actually saw in the first question that electron withdrawing groups made it less stable and made it more reactive, right? So like, you have to be able to reason your way through. Like in this case, we've lost a proton. What's going to stabilize our electrons? In the other case, I think of it as like, oh, we have an electrophilic center. which one of these is going to be the quickest to react. So you have to really think in the context of what the question is asking you. So in my opinion, the most acidic is going to be the one with the biggest electron withdrawing group. That's going to be able to stabilize the conjugate base better. So we're looking for something that has the most electron withdrawing group to stabilize the conjugate base. That's going to be the one that is the most acidic. So most acidic, let's see. We have an electron withdrawing group here, a strongly electron withdrawing group here, a lightly electron donating group, or a moderate electron donating group, and a light electron donating group. And then this is a partial positive, so an electron withdrawing group here too. So the most stable is going to be the one that has the electron densities pulled away the most. So I think this is going to be, it's order of increasing. So maybe I'm supposed to start at the lowest, but this is going to be the most acidic. And then the one that has the most electron donating is going to be the least acidic. So this is going to be the least acidic. So increasing acidity, less to most. So I think technically this would be 1. That's the least acidic because it has the strongest electron donating group. And then we can compare between these two. This is the only other electron donating group. So then this is the next most acidic, more basic. And then we have, let's see, this is electron withdrawing. This is... So we just have to look between the halide and the I just blanked on this name, the ketone here. And the halide is less electron withdrawing than the carbonyl group. So I would actually say then we have this, and then this, and then number 5, the most acidic right here. So this is the least. I'm going to redraw it out because I think it's kind of confusing to number it. So I'm going to draw it from least acidic to most acidic. So I'm just going to put carboxylic acid here, and then nitro. And then the next most acidic is, I guess we should say that's less acidic than a carboxylic acid with the carbonyl group. And then we have I forgot the methyl. The methyl group goes right in between these. So you have this one, then the methyl, then the first electron. Oh no, I'm all out of order. See, this is why I shouldn't do these videos late at night. Then we have the bromo. I forgot 2 of them. And then we have our ester, or our ketone. And then we have our most electron withdrawing group. So this is the least acidic. This is the most acidic. And the reason for that is because it's the least acidic with the most electron donating group. The most acidic has the withdrawing group. I realized I did that totally wrong. I drew that as a nitro. I think it's probably I did not sleep very well last night and my brain is not functioning optimally. So I hope I'm not confusing you more. I hope this is helpful for you. Okay, I really am so sorry. Please forgive me. The week of my defense is, or my dissertation is due coming up in a few days. So I have not been sleeping very well and I've been working a lot. So really, I'm so sorry for how I'm stumbling over words and how I'm drawing this out crazy. Okay, so propose a synthesis for the following pathway. So we're going from a double bond to a carboxylic acid. One thing I like to do is number my carbons to see, are we adding any carbons? Because if we're adding carbons, that means Grignard to me. Well, it doesn't look like we're adding any carbons. It looks like it's staying the same. So how do we get to a carboxylic acid? Well, usually we can get to a carboxylic acid from any of the carboxylic acid derivatives, but also if you go way, way back to like chapter 12, you can oxidize an alcohol, and we know how to add alcohols to double bonds. That's like one of the first reactions that we learn, right? So I would want to add an alcohol here, and then I would want to oxidize it. So that would be my plan to get from here to here. Though we don't add any carbons if we added an alcohol there, and if we oxidize a primary alcohol, it can go all the way to a carboxylic acid as long as we use the right reagent. So then that's the next question I'm asking myself is like, well, what reagent do we use to get from here to here? And there's only one way that you can add an alcohol on the less substituted side. That's anti-Markovnikov. We only learned one anti-Markovnikov way, and that's hydroboration oxidation. So BH3, THF, followed by, I think it's NaOH and H2O2, would be how I get from here to here. And then to oxidize it, you can use, let me see, which one? There's one that goes to an aldehyde. I think it's PCC goes to an aldehyde. So we can't use PCC because this would take a primary alcohol to an aldehyde. But if we use Jones reagent, so that would be sodium Cr2O7 and H2SO4, I think. That will go all the way, or we could use KMNO4. KMNO4 would also work to oxidize that. Oh, there you go. That would take us from here to here and then here to here. Okay, let's see. Oh, more synthetic pathways. These are kind of fun. I actually really like these. So let's see. We're adding an alcohol. We're not adding a carbon on here. So when I look at this, I think how can I get to an alcohol from a toluene? And what I would actually probably do is use, I think you could do KMNO4 to get to a carboxylic acid. Remember, we learned that a carboxylic acid, you can always form a carboxylic acid if you have an R chain here, as long as it's not like, I think, an alkene or an alkyne, and that'll get you a carboxylic acid. And then you could reduce that with LAH, or you can't use NaBH4 because it's too hard to reduce that, I believe. So, yeah, I think that's a synthetic pathway I would use. There's probably a lot of other pathways you could use, but that's the one that stands out to me. And then actually for this next one, if I see bromine in an alcohol, I'm thinking Grignard, and that's reinforced by the fact that there is not a carbon here, but there is a carbon here. So it's like carbon-carbon bond, we've got a bromine, we've got an alcohol. All those things send off the signal for Grignard in my mind, because Grignard is one of the only ways we've learned to make carbon-carbon bonds, and they usually end up with an alcohol, and you have to start with some kind of bromine. So that's going to be my first thing, is turn this into a Grignard reagent. And then we're only adding one carbon, and that carbon has to have a place to attack. So I actually think it's probably this. Let's see. No. This is our carbon that we're adding. We're only adding one carbon. So I actually think it's this. That makes more sense. We're adding one carbon, and this structure has one carbon. So then our Grignard will attack right here and kick this up, and you'll get your O minus, H, and H. And then if you add H plus to that, it will become OH, H, and H. So I initially was thinking like, oh, we're only adding one carbon. So I drew this structure. And the thing that made me realize like that wouldn't make sense is because there's two carbons here and we're only adding one. But if you do that, one thing that I always do is I try to reverse work my reaction, right? So like this was my suspicion that this was work. So then I worked it. I don't just like put the reagents I think will work. I always try to then go ahead and work them out. So if this was what we had done with the Grignard, what would have ended up happening is we would have gotten an O minus and a CH3 and then a hydrogen. So that wouldn't have worked. So even if I had left with what I thought it was originally, once I actually worked the product out, that wouldn't work. And so I build that in to kind of catch myself. So when I was doing this, I was thinking, oh, we're making this MGBR and I think this would work. So I'm going to work it out and see if it would work, and it does. So now I can go ahead and say that we would just add magnesium here. And then to get here, we would add formaldehyde. And then for step 1, and then step 2, we would do H+. You can't forget your H+, or else it'll just be an O-. It won't be an alcohol. Okay, draw the mechanism and predict the attack of the following reaction. Name each step. So when I see this, I'm like, hey, this is going to attack and come here. So that's the nucleophilic attack step. And you have your NH, CH2, CH3. And then whenever I do these reactions, I always do the initial attack. And then I ask myself, is there a good leaving group? And the answer is there is a good leaving group. Chlorine's a good leaving group. This will possibly get deprotonated first before this happens, but just for brevity, I'm going to go ahead and show this happening. And then you would get a deprotonation, and you've made your amide. I guess we are supposed to label every step, so I'll say proton transfer on this one. Proton transfer or loss of proton, either one of those is okay. And it would probably come from your Cl minus over here. And so you'd actually get this plus HCl and water, or whatever else is in there. Or your, there's 2 amines actually, so your amine that's present could also take a proton. I mean, it could kind of happen from anywhere. So I won't grade too hard on that question. Okay. What would the final product look like if the primary amine below was replaced with 2 equivalents of the secondary amine shown below? So I think the only difference is instead of having, I think I might have actually drawn this out wrong. Oh yeah, I left this hydrogen. So the only difference is instead of having that hydrogen there, it'll be just like an O2R group. So I'm going to draw that for you. What was the starting material? Cl. So your amine comes in attack and it kicks up and you get O minus with the Cl. You're in this H plus. This will come down, kick out. That's your loss of your leaving group. And then you have O and H. And that's positive, and you'll lose your proton, or you'll get your proton transfer, and you have in like that. And so for me, whenever, oh shoot, I was off camera that whole time. So for me, whenever I do, this is your final answer. Whenever I do these, pretty much all carboxylic acid derivatives, if it starts with chlorine and you attack with like an RH, so this could be NH2H, NRHH, ROH, any of these, really what's going to happen is this is going to replace the chlorine, whatever is in these lines. So if you have an acid chloride and you react it with an alcohol, and whatever other conditions you get an ester. If you react it with amines, an excess amine, you get, it'd be NH3, you'd get NH2. If you have, like what we have here in R2H, you got in R2. That's NH2. So, it's like whatever is here, you're going to lose a proton, but ultimately this is going to replace the chlorine. So just a substitution reaction is all you're seeing. Very, very similar to like SN2. Okay, this is Fischer esterification. I'm pretty sure Dr. Krauss mentioned that this was going to be on your quiz. So I would pay attention to the mechanism here. So as always, it attacks at the carbonyl carbon. That kicks up. We have our OH, we have OH, and then tert butoxide. And then this could get deprotonated either by water or an intra-electron proton transfer, however you want to do it. So OH, OH, and then O, and your tert butoxide. And now it does not matter which one of these, but one of these will get protonated one step more from the acid in solution. I'm going to pick this one for ease of my final product drawing, but either of those alcohols is equivalently the same, so it doesn't matter. There's only one lone pair there. And then these lone pairs will come down. This is now a good leaving group, and it will kick it out. So it's the same basic steps that we've seen over and over. The nucleophile attacks the carbonyl carbon. There's not a good leaving group, so then a good leaving group is actually generated. And then the same thing, it kicks it out. So then we have OH plus, our R group over here, and our tert butoxide over here, plus the OH2 in solution, and then that will come and deprotonate. The OH2 will come and steal this. That's a bad arrow, sorry. And you end up with an ester. And I'm pretty sure we did Fischer esterification in an earlier chapter. But yeah, that's the overall reaction mechanism here. And then if you add acid to that, acid and water, it will convert it back to the carboxylic acid. That's called hydrolyzing back. And you can convert anything back to a carboxylic acid. Any of these carboxylic acid derivatives can be converted back with either water or acid and water, a combination of them depending on which derivative it is. Okay, so this next question, draw the mechanism and predict the product of the following reaction. Well, one thing with esters is, first of all, we've already done this reaction. You've seen this, but it comes up, kicks up, and then this comes back down and kicks out. So I'm not going to draw that all out because it's getting later and later, and I'm getting tireder and tireder. But this group has left, and this actually has recovered. Sorry. And then I need to number 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Carbon 2 has, oh shoot, I did it in the wrong place. This is why you should use pencil. 1, 2, 3, 4. 1, 2, 3, 4. Carbon 2 has a methyl group and 3 has a methyl group. Okay. But then actually, if you have excess of that, it's going to come and attack again. So because this initial one, the leaving group leaves, you get a carbonyl group restored. So actually, it's probably going to go one more time and kick up, and you'll get O minus. One, 2, 3, 4, 2, and 3. And then that will get protonated to become an alcohol. So I actually think this would be your final product, which is kind of chaos. But it could stop here if you only had one equivalent, I think. And it might be, this is bulky, so it might be hard. But ultimately, if I see an ester and I see a Grignard reagent, I'm going to assume that that's going to react twice. And all you need to make this Grignard reagent is bromine with magnesium, and then it will make the MgBr. What reagent would you use if you wanted to make an aldehyde rather than an alcohol product? So for this, I would actually, whenever I see like ester, because that's our starting product, ester to aldehyde, if you just use like any old reducing agent, it's the like lithium aluminum hydride, that's going to take it back, right? All the way back to an alcohol. But we learned a new one this chapter. It's called it's called a few things. It's sometimes called Diol H, It's also sometimes just called DIBA. Its full name is diisobutyl aluminum hydride. So diisobutyl aluminum hydride, or A hydride. So basically what that is like, you've learned a lithium hydride. This is LAH. This is like got so many hydrogens, it's strong, it can react with anything, and it'll be like offset by the lithium. DIBA is 2 R groups. I think they look like this, with just 1 hydrogen on it. So because it only has the 1 hydrogen, it's not as strong of a reaction. So it can take the ester to the aldehyde and stop. So I would use Diba-H or Diba to go from the ester to the aldehyde. But you do need to keep that at low temperatures so that it doesn't overreact and go to further reduction. Okay. Oh, look, here's the same kind of question. Whenever I see Diba with an ester, I'm like, heck yes, I know what's going to happen here. So I'm going to do the products of this reaction, and I'm going to talk about how I got them, but I'm not going to actually work them out for you, mostly because I'm very, very tired, and y'all have a quiz tomorrow. But hopefully this looks familiar to you. We actually already saw this reaction. This makes a succinic anhydride. I drew out the reaction for you right here. Succinic anhydride. So this is succinic acid. It reacts with itself in heat to make succinic anhydride. Let's see. If we react an ester with, I'm just going to leave this as an R group over here, with an acid, I think it would become a carboxylic acid. And then with this, in pyridine, the pyridine would deprotonate that, making it negative. And you have this CH3C. This is your R group. So it's going to come attack, kick up, come back down, kick that out, and you'll get this oxygen is where the bond forms between here and this chlorine, the leaving group left. So you'll get an anhydride. With whatever the R group was over here first. So that'll have that R group will still be on there. Hopefully you remember this one. This is actually just a review of your earlier chapter, but LAH takes a carboxylic acid to have 5 bonds to this carbon. I'm losing my mind. OH. So it goes all the way to a primary alcohol. This, I actually think, will come and attack here, come down, come back here, and kick this out, and you'll end up with there's an oxygen between these 2 things because the bond happens through the oxygen. I almost lost that. And then like this. So again, for this one here and this one, you have your nucleophile with a good leaving group. So like your electrophile with a good leaving group. So in this case, it was this thing. So this is going to swap out for whatever your nucleophile is. And in this case, our nucleophile was that, right? So all I did was trade out that chlorine for this group. And then same thing here. This is our good leaving group. So this good leaving group is going to leave, and this is going to attach, and then it just gets deprotonated. So that's all that we're doing here, over and over, literally. Again, here's our good leaving group. Here's our nucleophile. So we're just going to swap that out, and you'll get nitrogen with 2 phenols, and it got deprotonated. Even if you can't see that substitution, this comes in, then comes back, kicks that out. That's how that reaction happens. So it's the same thing we've seen over and over. Oh, this last question I really like. It says, starting with phenol, devise a synthesis for acetaminophen And then it gives you a hint on how you can reduce a nitro group. So that's also a hint that you can use a nitro group. So acetaminophen, that's orthometapara, that's para substitution. So alcohol is an electron donating group, so it's an ortho-para substitutor. So we can actually just do H2SO4 and nitro to get, we'll get a combination of the two of these. If you're doing it in real life, you would get both of these. And you would just do a purification reaction and keep this one and get rid of that one, do something else with it. And then we can reduce this with zinc, HCl, and NaOH. And you might be like, wait, we've never done a reduction on a nitro group before. That's true, but all you do with reduction is replace oxygens with hydrogens, right? Like replace bonds with oxygen to bond to hydrogen. So if we're reducing this, then we'll end up with NH2. And then this is now going to be our nucleophile, and we just need something with a good leaving group, and then our nucleophile can attack, come here, come back down, kick that out, substitute out, and we'll get OH in. There we go. I hope that was helpful to you. Sorry for the mistakes I made. I was very tired, but hopefully this is helpful to you before your quiz tomorrow.